This is the first video for section 1.3, the derivative of a function at a point. So let's recall our expression for average velocity on the interval a to a plus h if I'm given a function f. It is f of a plus h minus f of a over a plus h minus a, which simplifies, of course, to f of a plus h minus f of a over h. Now, what we're interested in this section is the instantaneous rate of change of f of x at a, and that's what we're going to call the derivative of f at a. And so our definition is that f prime of a, the derivative of f at a, is the limit as h goes to 0 of f of a plus h minus f of a over h. So remember, instantaneous rate of change was the average rate of change on a smaller and smaller time interval. So that's what happens when h goes to 0. We take this average velocity quantity and we let our time interval get really small, and that is our instantaneous velocity or instantaneous rate of change if f is not a position function. So it should be noted that this quantity may not exist, and we will spend some time thinking about when this quantity does not exist. But if it does, if f prime of a does exist, then we say that f is differentiable at a. So what's the geometric interpretation of the derivative? Well, recall that the average velocity, which was f of a plus h minus f of a over h, we could only take it on the interval from a to a plus h if h was not 0. So we need an interval with a non-zero length. So here I have a function f of x, and I have a and a plus h, and the corresponding y values marked. And so f of a plus h minus f of a, that's my change in function values, in other words, my rise. And my h is just a plus h minus a, or my run, and that's exactly the slope of the line connecting a f of a to a plus h f of a plus h, and we call that line a secant line. So average velocity is the slope of the secant line between a and a plus h. So since the derivative is the limit as h goes to 0 of the slope of the secant line, what happens as h goes to 0? In other words, what is the limit as h goes to 0 of f of a plus h minus f of a over h even measuring? So here's my first scenario. So h is not 0. So as we take h going smaller and smaller and smaller, a plus h is going to get closer and closer to a, and what we end up with is just the tangent line at a. And since we're measuring slopes, what we end up measuring is the slope of the tangent line to f at a. And indeed, that's what I have written here, that the limit as h goes to 0 of f of a plus h minus f of a over h measures the slope of the tangent line to f of x at a. So in conclusion, f prime of a, which again is the derivative of f at a, that's just notation, that is the slope of the tangent line to f of x at x equals a. And you should remember that, and we will review that ad nauseum.